Good morning, everyone, or shall I say good lunch to those who are eating either here or at home. What we are going to do today in the Discrete Maths 2 course is to wind up our discussion of how to solve systems of linear equation. In particular, we are going to look at a special type of linear equations where the vector of constants is the zero vector. So we're going to solve linear equations of the form a1x1 plus blah, blah, blah equals to 0. Excellent. And we will see also a recap of some of the things that you've already seen in Discrete Maths 1, namely matrix operations. This will serve as a warm-up for introducing a new operation about matrices that essentially plays the role of 1 over A, where A is a number, and this is called inverting a matrix, finding the inverse of a matrix. As usual, before getting to the new material, let's warm up, let's get our neurons buzzing by answering a couple of questions. Before we get started with answering questions, actually, let me thank everyone for the comments I received in the midterm evaluation. It sort of brought me back to my times as a student at the University of Pisa, where I got all the marks, all the pass marks from the lowest to the highest in all of my courses. And this is actually a non-trivial feat because the marks there go, the pass marks are from 18 to 30 with praise. So it's not like here, sort of from 5 to 10. It's easy to get them all. But from 18 to 30 with praise, well, it takes quite a few courses. And it also shows you that perhaps I was not as good a student as you are. Actually, did I say that on YouTube? I did. Oh, sorry. Forget about that. I'm supposed to be a role model here, for some, at least. So, well, anyway, the message to say is that whatever you're experiencing now, I experienced it myself when it was my turn to be you. God forbid if it ever becomes your turn to be me, because you cannot make everyone happy. That's why you get all the marks from 1 to 5. I did get once as well, and I'm not afraid of saying that. Okay, so back to answering questions. So one of the things we saw last time was that the way we go about solving systems of linear equations is to put matrices to sort of transform systems of equations into matrix form. These are the so-called augmented matrices. And we try to apply the elementary row operations to put these matrices into a nice form. And this nice form is the so-called row echelon form. And there is an even nicer form, which is the reduced row echelon form. So just to remind ourselves of what it takes for a matrix to be in row echelon form, here are 3 examples. 3 is the magic number, so let's stick to it, of 3 matrices. And I ask you, which one of those are in row echelon form? Okay, so somebody said none of them. Somebody said the middle one. Now, I don't know what you're saying at home. I cannot hear you, but I'm sure you have your own take on this. So let's look at the first matrix here, the one I'm pointing to. Okay, so what could be wrong for this matrix to be in row echelon form? If you were to convince me that this matrix is in row echelon form, what is it that you would not succeed? Okay, one of your colleagues here said, well, the second row actually doesn't have a leading one. This means that as you travel along this row, the first non-zero entry you find is a 2. That's not allowed. Spider sense is tingling. This is not in row echelon form. However, we can put it in row echelon form very easily. What is it that we do? Multiply the second row by half. And if we do that, we get something which is in row echelon form. How about the second one? Is it in row echelon form? Yeah, your colleagues here are saying yes. Why? Okay, sort of the first row is a leading one straight away, so far so good. The second row also has a leading one, and moreover, it comes to the right of the leading one on the row above. That's good. Remember, the leading ones, should form a staircase pattern. So you should actually move like this. Okay, fantastic. The last row is a row of zeros. Does it matter? No, it's in the right place, because all of the rows of zeros should be at the bottom of the matrix. If they are not, we can put them there by swapping rows. Fantastic. So this is in row echelon form. How about this one? Well, it's not, because it doesn't have this staircase pattern. So the leading one on the second row is not to the right of the leading row of the leading one on the row above. It's actually right below it. What we have to do in order to put this matrix into row echelon form? Subtract, as one of your colleagues here is saying, you subtract the first row from the second. And you get a row of zeros at the bottom, which is cool, which is okay. So probably you know what I'm about to ask here. Is this one in reduced row echelon form? Some of your colleagues here are saying no. Why not? What does it take for a matrix in row echelon form to be reduced? We cook it for 45 minutes at high temperature? No, sorry, that's for sauces. It's not for matrices. Okay, well, in each column where there is a leading one, the leading one should be the only non-zero entry. So this seems to be kosher. This seems to be cool. So every leading one is the only non-zero entry in its column. So this is actually reduced. It has two free variables corresponding to x2. So if you will look at these matrices representing a system of linear equations without the constant coefficients, then x2 and x4, which correspond to the second and the fourth column, would be free variables that you could use to parameterize the solutions in the solution set. Okay, well, assuming that there is no inconsistency in the last row, of course. Okay, any doubt about this? So the only thing that one needs to do is just, if somebody asks you, is this in row echelon form, you just look at the conditions and you check whether they're all satisfied. Excellent. So we'll answer more questions later on. So today I'm going to divide the question answering into two parts. So this is really going to be like a game of football. So we have a first half and a second half also for the question answering. So let's refresh our memory of the algorithm that we followed and that actually Gauss and Gauss-Jordan taught us in order to solve a system of linear equations systematically. In fact, actually, this method, even though it's attributed to Gauss and Jordan, was actually found by Chinese mathematicians about 2,000 years before. So it's not an entirely new thing, where new means 250 years old. So it's much older than that, at least in spirit. Then Gauss and Jordan actually made the method completely formal. Okay, so we start from a system of linear equations. And the first thing we do is we turn it into matrix form. And we generate an augmented matrix out of that. Once we've done that, we feed the augmented matrix to a nice Gauss-Jordan routine. Okay, well, basically what this does is it puts the matrix corresponding to the system of equations into row echelon form or reduced row echelon form, depending on what you like best. So the outcome is our possibly reduced row echelon matrix. So what do we do next? How do we determine whether this system has any solution? Okay, so there is a decision point here. When is it that the system does not have any solution? Okay, so your colleague here is saying, as you're saying most surely at home while you're listening to this lecture, or that the telltale sign for an inconsistent system is when you have a row of zeros that ends, but after the solid line, you have a non-zero value. So in fact, since we can always divide a row by, multiply it by any non-zero number, this row is always going to be something of this form. As you have zeros, I wrote 3, but it could be arbitrarily many zeros, and then you have a 1 after the solid one. Is there such a thing? Well, if the answer is yes, then we are unhappy, because the system has no solution. No soul, no sun, like here at this moment in time, or sort of some approximation of it today. Well, what if the answer is no? We don't have a row like this. Your colleagues here are saying you can either have infinitely many or one solution. When is it that the system has infinitely many solutions? When there are free variables, as one of your colleagues is saying. And when do free variables exist? So it's got to do with the number of leading ones that tell you what the rank of the matrix is, as opposed to the number of columns, which tells you how many variables there are in the system. So there's another decision point here. So let's assume that the system of equations has n variables. So we ask ourselves, is rank smaller than n? Well, this is an n. If the rank is smaller than n, what can we conclude? The number of leading ones is smaller than the number of variables. Then infinitely many solutions. If the answer is no, then how many solutions do we have? One, that's the other option. We are in our solar system. There is only one sun, one solution. Okay, so that's the algorithm. Now, let me ask you, have you asked yourselves, why is it okay to turn the system of linear equations into a matrix? Why is that okay? Why does the matrix actually represent the original system of equations? So in other words, why is step 1 kosher? So what we did, for instance, was to do something like this. So let's assume that I have a system of linear equations. That, for instance, it could be something of that form. And here you have x1 minus x2, say, equals to 2. looking at the recipe I cooked before. Okay, what we said was that, well, actually, this part here, we are going to represent as this matrix. 2, 4, 1, minus 1. We're going to take the first row, the first equation, and we get the first row. Look at the second equation, we get the second row. But why is that okay? Well, the reason why I'm asking you this question is because I would like to, actually, I would like you to refresh my memory as to what matrix multiplication actually does. What do I get if I multiply this matrix by this vector, x1, x2, which is nothing but a matrix with 2 rows and 1 column? What is it that I get? You get exactly the linear equation, the linear combination that we were looking at. So look at the 2x1 plus 4x2. That's exactly what we get by multiplying the first row with the column x1, x2. Because this is nothing but 2 times x1 plus 4 times x2. And if we do the same with the second one, we get x1 minus x2. You see, there is no magic. There's just matrix multiplication. That's why it's okay to represent the system of linear equations as a matrix. Okay, matrix multiplication is something that belongs to your past, but we are going to exercise our memory today. And now there is really sun outside, so we should all be happy. I am. Okay, excellent. So let's solve a system of linear equations, shall we? But I'm going to make it for you, perhaps a little bit different from the ones that you've seen before. So let's assume that I'm looking at this system here. Where actually the second equation has some parameters a, b, and c, where a and b are the multiplying coefficients for x and y, and c is an unspecified constant. So my question to you is the following. For what values of a, b, and c does the system have 0, 1, infinitely many solutions? Now, this may seem like a difficult exercise. Do you think it's difficult? Well, the only way to figure out is to try, isn't it? Otherwise, we cannot know whether it's difficult or not. Sometimes, I mean, you see something that looks very difficult and you try to solve it and you say, wow, piece of cake. On the other hand, some other times you look at something, you say, wow, that's easy. And then you try to solve it and you figure out, well, that's not so easy after all. It's been an open question since the beginning of humankind. So in that case, it's not particularly easy. So the only way to try is to figure out what these values are, whether it is difficult or not, is to try. And do we know how to solve a system of linear equations? Sure we do. We've just seen the algorithms. Some of you have it tattooed on their forearms. So let's do it. Okay, so what is the first step? We put this into matrix form. We just saw the algorithm before. And now what is the augmented matrix? 1, 1, A, B, 2, C. And what next? Oh, by the way, whenever I ask you a question, you can also answer in Icelandic or Danish if you like, or even Italian or French.
Well, we should be trying to get the zeros at the bottom.
Well, okay, so in general, what is it that we should be trying to do? We should try to get this matrix into row echelon form at the very least, isn't it? And to do so, it really doesn't matter. We don't need to know what A, B, and C are. We can consider them as variables, which we can work with. Okay, so what does the Gauss-Jordan algorithm tell us to do there? Okay, so if you look at the first row, we already have a leading one. Nothing to do. Okay, we look at the second row, there is an A there. What is it that we want to put instead of the A? A 0. So how do we do that? We multiply the first row by minus A, and we sum it to the second row. Let's see what happens. We take minus A, row 1, and we sum it to row 2. Okay, the first row doesn't change. We haven't done anything to it. What about the second one? Okay, we get A minus A, 0. Ding. B minus A, well, B minus A. That's all we know, isn't it? C minus 2A. And you know what? Now we can answer. When is it that this system of equations has 0 solutions?
0 solutions if it's inconsistent and there's a 0, 0, 1.
Absolutely. Okay, so there is a 0, 0, 1 at the bottom, or in general, there is a 0, 0, something different from 0. Okay, so when is it that this is 0? B minus A is 0 when B is equal to A. If B is equal to A and C is not equal to 2A, then we have a row that says 0, 0, something which is not 0. So in this case, no solution. Okay? Well, for those who don't like smileys or grumpies, let me write no solutions explicitly. Okay? So what is another possibility? Well, it could very well be that B is equal to A and C is equal to 2A. What do we know in this case? What happens to the last row? It's all 0. So in that case, how many solutions do we have? If the last row is all zeros, there is only one equation that basically says x plus y equals 2. This describes a line. And how many points are there on a line? Infinitely many. All the x and y that when summed together give you 2. There are a hell of a lot of those, uncountably many. So if this is the case, then you have infinitely many solutions. Okay, there's only one case left. Let's make it green. For those of you who don't want more than one solution, but they want one. Very often in life, it's actually a good thing to have only one choice. Otherwise, you have to choose, and that's bad. Søren Kierkegaard, the famous Danish philosopher from a while back, used to say, well, then you have to choose, and that's where anguish comes, the angst. Should I go that way or the other way? And, well, squeaky bums, you don't know what to choose because you're always afraid of making any mistakes. If you have only one solution, well, you have to take that one. Sorry. Or be happy that you have at least one, and exactly one. Okay, so when does this happen? Well, both of these cases that we considered apply when B is equal to A. When B is not equal to A, then what is it that you have? You have something which is non-zero there, and then you have only one solution. Because you just multiply by 1 over B minus A, and you get a 1 there, and then you know exactly what Y is going to be like. One solution. Okay, so if somebody at some point, for instance me, asks you, well, find values for some unspecified parameters that tell you when this system has no solution, one solution, or infinitely many solutions, then don't get scared. It's the same algorithm that you use when you actually compute with numbers. It's only more interesting because it's less boring. You have to think a little bit at the end. After you've reduced the matrix to row echelon form, you look at it and you say, okay, when is it that I get a row of zeros? When is it that I get a row that leads to inconsistency? For what values of the parameters? And when is it that I get only one solution? For what values of the parameters? It's algorithms, but then at the end you need to think a little bit, which is ideal because these exercises don't involve a lot of calculations. They just involve your brain cells. And you have lots of those. I think there are many more brain cells than patients, than the amount of patience for long calculations. At least if you are like me. And you have many more brain cells than I do, so you're younger and smarter. So don't get scared, use them. Any doubt about what we have just done? Hello? Okay, no, there is a no from the audience. I had heard the people from home actually say, no, we don't have any doubt. And if you have any doubt, ask on Piazza. You know that for some reason I'm going to be there. For some reason. Okay, excellent. Can we move on? Beautiful. I mean, you were wondering, is he not going to use any slides today? Yes, I am. And you know, one of the reasons why there are slides is also so that you don't have to write everything that I put on the slides. They are there, they're on the slides. You don't need to write them. You just need to think along with me in class. And in class also means at home while you're watching the lectures. That's what the lectures are for. So note down the important stuff, not everything. Otherwise, you will need a dictaphone, as in the old days. And you don't need one, because everything I say gets recorded. And this even includes the bullshit I may say every now and then. Whereas all of your questions don't get recorded. Well, they get recorded, but anonymously because I repeat them. So that everybody also at home can understand them. But they are questions from me to myself, so which might not do well for my mental health. Anyway, so let's look at the special type of linear equations, which are really nice. They are systems of so-called homogeneous linear equations. Now, what does homogeneous mean? It means the simple thing, the constant vector, all the equations that we have, they're of the form linear combination equals 0. So the constant vector is all zeros. Now, question, can such a system of equations have no solutions whatsoever? Or are we always guaranteed that there is always at least one solution? That's not a trick question. Consider a simple case. If I tell you, does the system of equation consisting only of one equation, 2x plus y equals 0. Does it have an obvious solution that you can find out without calculating anything? Yes. Which one is it? Set everything to 0. If I say x1 is 0, x2 is 0, xn is 0, then surely everything is 0, isn't it? Because a1 times 0 gives me 0, a2 times 0 gives me 0. Everything gives me 0. If I sum 0 together many, many times, I get 0. This is the algorithm that I hoped my daughter will be following yesterday when she was singing along to get sweets. And instead, it was not the case. She was getting a non-zero amount at each place, and then the result was a non-zero amount. I was hoping for a 0 amount at each shop. These are the x1, x2, xn's. These are all the shops that she visited, far too many of them. And at the end, the result was, yeah, diabetes or something of that sort. Not 0, which would have been a nice thing. Okay, so these systems are nice because they are always consistent. So what is the interesting question for these systems? Well, when does this system have infinitely many solutions? Since it always has at least one, we want to know whether it has infinitely many or not.
Wait, it has one solution when everything is 0.
Okay, there's one solution. The question is, wait, it has one solution when everything is 0. Well, that's always a solution. The question is whether there is some other solution which is not 0. Okay? Well, sometimes you can actually tell just by looking at it whether the system has infinitely many solutions or not. And the test is very easy. In fact, it's so easy, well, it's a sufficient condition. It's not a necessary condition. But if you see it, you will know for sure that the system has infinitely many solutions. So think about it. We just said that I could, of course, show you the condition, but it's nicer if you actually discover it yourself because it's staring at you, and it's not me, even though I'm staring at you right now. So think about it. What is it that we said before? If the rank of the matrix is smaller than the number of variables, then there are infinitely many solutions, provided you don't have any inconsistent row. But here there are no inconsistent rows. They cannot be. The system is always consistent. So suppose I have, say, 3 equations in 5 variables. Do you think that system is going to have one solution? How many leading ones can you have at most if you have 3 equations, 3 rows? You can have 3, but there are 5 variables. So you're going to have at least 2 free variables. So infinitely many solutions. In fact, there you are. A homogeneous system that has more variables than equations always has infinitely many solutions. You don't need to calculate. Now, that's not true if the system is not homogeneous, because you could have an inconsistency somewhere. But here there cannot be an inconsistency because the 0 vector is always a solution. Okay? And as I said, that's on the slide anyway. So let me show you one of the reasons why homogeneous systems of equations are very nice. And this is not so much important for this course in itself. It's important in the context of more complicated linear algebra that we will not have time to cover in the course. But for me, it's an excuse to make you refresh some operations, the properties of some basic operations on matrices that you all know and love from Discrete Maths 1. So suppose that I have a system of homogeneous equations, and let me represent it in matrix form. So I have a matrix A, which is the matrix of coefficients, And then I have a vector x, and I'm trying to solve this equation ax equals 0. Now, A is a matrix, and x is basically the vector of variables here, of unknowns, of the appropriate size. And we've already seen, actually, that building the augmented matrix is nothing but multiplying the matrix of coefficients A by this unknown vector. We did it on an example before. If you're not convinced, we did it here. Let's scroll down here. Yeah, that's what we did here. That's the A, and that's the vector. So one thing that we already figured out is one property of this system of equations. If I take x to be the 0 vector, that's a solution. Now, suppose that a vector x1 and a vector x2 are solutions of, let me call it star, this equation here. What can I say about the vector x1 plus x2? What about? One of your colleagues is saying that's also a solution. So the space of solutions is closed under addition. Give me two solutions, I sum them together, I get a solution. That's absolutely right. But why? Well, let's see. If I calculate A times x1 plus x2, what is this equal to? Now, if A, x1, and x2 were numbers, how would you simplify this expression? Okay, here we are not talking matrix algebra, we are talking about elementary school maths. Okay, so one thing that I would do is to distribute, isn't it? This would be the same as ax1 plus ax2. Isn't that right? And actually, this is one of the many properties of multiplication and sum over numbers that matrices actually also satisfy. But now what is it that we said? We said that x1 was a solution to the homogeneous system. So this means that ax1 is equal to what? 0. ax2 is also x2 is also a solution, so ax2 is also 0. But 0 plus 0, even for vectors, last time we looked at it, is equal to 0. So x1 plus x2 is also a solution. The only thing that we used was a property of matrix multiplication. If you take A times the sum of two matrices, you can distribute. But there's more. There's a third property. Okay? Suppose X is a solution. To star. And let A be a real number. Okay, so how about A times X. Now, what kind of object is this? It's a vector. So let me extend the page. So if X is equal to X1, blah, 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 Xn, what is A of X? A times X. Absolutely, you multiply everything by A. That's an operation on matrices as well. You can multiply every entry in a matrix by a real number. Okay, so let's try to see what this thing is. This thing is actually equal to A times X. But then what is this? AX is equal to 0 because X is a solution. So we have A times the 0 vector, but A times the 0 vector is the 0 vector. Doesn't matter what you multiply zeros with, you still get zeros. So what is the message? The message is that if somebody gives you a solution to a homogeneous system of linear equations, you can multiply that solution by an arbitrary number pointwise, and you still get the solution. So for those of you who are following or are interested in more general topics in linear algebra, this gives a very important structure to the collection of solutions to a system of linear equations. It's something that is called a vector space, which is really what linear algebra is about. That's why we are not going to touch on it at all in this course, because this course is really about sort of linear algebra 101 minus the 1. So it's the 0 vector. This part of the course is the 0 vector of linear algebra. It's linear algebra 0, 0, 0. But it's hopefully not inconsistent. It's just a pointer for an infinite amount of future studies. Okay. So, so far so good, I hope. Now we take a break. After the break, you will teach me how to invert matrices. Or, in other words, we'll teach each other how to invert matrices, which is the missing operation over matrices that you didn't see in discrete maths 1.